Welcome to this masterclass on pressure vessel fabrication. We will bridge the gap between engineering codes and the ground-level physics of welding, covering design, materials, and fabrication for pressure vessels. Let's explore the anatomy of containment. Key components include the cylindrical shell, dished ends or heads, supports like saddles or skirts, and nozzles, inlets, and outlets, which require critical reinforcement. The main enemy in containment is stress. Circumferential, or hoop stress, is the critical force trying to split the cylinder along its length. Longitudinal stress tries to pop the dished ends off. Design tensile stress is based on yield and ultimate tensile strength. Welded joint efficiency, or ETA, is the ratio of joint strength to parent material strength. A perfect weld has an efficiency of 100%. Due to the difficulty in achieving absolute integrity, we often design for efficiencies between 75 and 85%, requiring thicker plates to compensate. Selecting the right alloy is crucial. Ferritic steels are used for general containment. Austenitic steels or stainless are suitable for corrosive or sanitary environments due to their ductility and chemical resistance. Aluminum alloys are ideal for cryogenic or lightweight uses. Extreme temperatures introduce the threat of creep, a slow, continuous plastic deformation under constant stress. Creep-resistant alloys are essential for high-pressure lines. Codes require factoring in the 100,000-hour creep rupture strength. Material traceability is essential. The chain of custody begins with hard stamping at the mill, followed by certification. The equipment manufacturer verifies test pieces before machining. The final component receives a full traceability dossier. If the paperwork fails, the vessel is scrapped. Flanges and facings dictate how pipes connect and seal. Weld neck flanges offer superior integrity. Slip-on flanges are lower cost, but less structurally robust. Sealing faces range from the concentrated pressure of a raised face to the metal-to-metal seal of a ring-type joint for extreme pressures. Cutting a nozzle hole destroys hoop stress continuity. This lost strength must be restored using reinforcing pads, heavy forged nozzles, or weld-ultents, which provide the necessary material compensation and structural integrity. Weld prep geometry is critical. The root face and root gap ensure full penetration without burn-through. Misalignment in the prep geometrically guarantees a stress riser. Alignment tolerances are extremely tight, at most 5 mm. We use different welding processes based on application. SMAW is versatile for field repair. MIG and FCAW are fast for shop fabrication. TIG provides absolute precision for high-pressure work, and SAW offers massive deposition for automated longitudinal and circumferential seams. The heat-affected zone, or HAZ, is the area adjacent to the weldment. The extreme thermal gradient permanently alters the metal's microstructure, making the HAZ brittle and susceptible to cracking. Hardness testing is required to map these changes. Blueprint weld symbols communicate precise welding instructions. The reference line anchors the symbol, and the symbol's position relative to the line indicates whether to weld the arrow side or the other side. Key profiles include V, bevel, and U-grooves. Quality assurance includes visual and dimensional checks for defects. Surface misalignment creates immense discontinuity stress. Bulging or distortion is caused by poor fit-up. Undercut acts as a severe stress riser, and excessive grinding reduces the effective wall thickness below the minimum. Non-destructive testing confirms weld integrity. Radiography, or RT, uses X-rays to find internal volumetric flaws like porosity and slag. Ultrasonic testing, UT, uses sound waves to find planar defects, like tight cracks, often used where RT film placement is difficult. The hydrostatic test is the final exam. The vessel is filled with water and pressurized to an overpressure state, typically 150% of design pressure, for 30 minutes. We use water because liquids are incompressible. If the vessel ruptures, the pressure instantly drops to zero, preventing the catastrophic explosive energy release of compressed gas. This marks the proof of mastery, going from code to arc to stamp, and the vessel is certified.